welcome back to another one of my videos. Today we're going to be discussing the heat diffusion equation and more importantly how to derive the heat diffusion equation. So in order to do that, we're going to start with some differential volume with dimensions delta x, delta y, and delta z. And into this differential volume we have heat flows of qx, qy, and qz. And out of it we also have heat flows of qx plus delta x, qy plus delta y, and qz plus delta z. And so in order to derive this equation, we need to first derive certain equations for this qx plus delta x. So to do that, we're going to use a Taylor series expansion. So we're going to say qx plus delta x is equal to the original heat flow, qx, plus the change in qx as it relates to the position, times the total length that it travels, which is dx. And so now we can do this for qy plus delta y is equal to qy plus as respects to delta y times the length it travels, dy. We're going to have qz plus delta z is equal to qz plus dqz over dz times the distance it travels dz. So now that we have all these, we want to figure out some way to relate them into one equation. So in order to do that, we're going to use energy generation rate and energy storage rate. So the reason that qx plus delta x is different from qx is because this differential volume has some energy storage rate, which is E dot G, and some energy storage rate, which is E dot ST. And so we want to use an equation that takes these into account and be able to substitute them for qx and qx plus delta x. So in order to do that, we're going to do an energy balance where energy rate in minus the energy rate out plus the energy generation rate has to equal the energy storage rate. And so now that we have the energy generation and energy storage in an equation, we need to figure out what these actually are. And thankfully we know this already. The energy generation rate is going to be equal to q dot dx, dy, dz. So basically q dot is the amount of energy generation per volume. And as you can see, dx, dy, dz is the volume of this rectangular prism. So now that we have the energy generation rate, we want to know the energy storage rate, which is going to be equal to the density times the heat capacity of this fluid times differential temperature with respect to time times dx, dy, dz. And so this is going to be the energy storage rate per volume times the volume of the geometric shape again. And so now that we have these two in, we need to figure out what E dot in and E dot out are. So as you can see, the only heat flows we have in are qx, qy, and qz, which means the energy rate in must be equal to the sum of qx, qy, and qz. And similarly, the energy rate out has to be equal to qx plus delta x plus qy plus delta y plus qz plus delta z. So now we have terms for each of these and how they relate to the differential volume as well as the heat flows. So now we can simplify these all into this equation up here. So the first step in combining this equation is to figure out what the energy in minus the energy rate out is. And so to do that, we can say qx plus qy plus qz minus qx plus delta x minus qy plus delta y minus qz plus delta z. And from our Taylor expansion, we have how qx plus delta x relates to qx. So we can go ahead and plug that in now. And I'm going to go ahead and put like terms next to each other as well. So we have qx minus qx plus dqx dx plus qy minus qy plus differential qy as it relates to y times dy plus qz minus qz plus differential qz as it relates to z dz. So now, as you can see, we have terms that can cancel out. This qx can cancel, qy can cancel, and qz can cancel. So this leaves us with the energy rate in minus energy rate out is going to be equal to negative partial derivative of qx as it relates to x times dx minus the partial derivative of qy as it relates to y dy minus the partial derivative of qz as it relates to z dz. So this will massively simplify our energy balance equation. We can now, from here, we can go ahead and simplify the other terms. So now we know what the energy rate in minus the energy rate out is. I'm going to go ahead and rewrite the entire energy balance equation. So we have E in minus E out plus EG equals EST. So for this, we just found this negative partial derivative of qx as it relates to x dx minus partial derivative of qy as it relates to y dy minus partial derivative of qz as it relates to z dz. And then to this, we're going to add q dot dx dy dz, and that's all going to be equal to rho cp partial derivative of time as it relates, or partial derivative of temperature as it relates to time times dx dy dz. And so now what we're going to do is use Fourier's law to make these partial derivatives into something that we can work with a little more easily. So Fourier's law states that q double prime x, aka the heat, or rather qx, the heat flow, is going to be equal to q double prime x, which is the heat flux, times the area. So qx is going to be equal to negative k partial derivative of t as it relates to x times dy dz. And we know that the area here is dy dz because that's the only term that is not using dx. And so now we can do the same thing for qy and qz. So we know that qy is going to be equal to negative k partial derivative of temperature as it relates to y of dx dz, and qz is going to be equal to negative k partial derivative of temperature as it relates to z dx dy. So as you can see, by doing this and plugging this in inside of the derivative, we can get a second derivative of temperature as it relates to x, and now every term will have dx, dy, dz, and we can divide that across. So let's go ahead and plug everything in. So first of all, because we're plugging in the k, or the negative k, these negatives will cancel and will become a positive. So we'll get the partial derivative with respect to x of k, partial derivative of t with respect to x, dx, dy, dz. And those can come out immediately because they're concepts. Then we're going to do the same thing for y. And the same thing for z. And then we're still going to add this q dot, dx, dy, dz, and it's going to be equal to rho Cp, partial derivative of temperature as it relates to time, dx, dy, dz. And so now we can just easily cancel all of those volume terms, and we're left with a much more simple equation of the second derivative of temperature as it relates to x. And then this k can come out because it's a constant. Do the same thing for y. And the same thing for z. Now all we're left here is q dot, and it's going to be equal to rho Cp, partial derivative of temperature as it relates to time. And so now we can divide this k across, and we're left with q over k and rho Cp over k. But we know that rho Cp over k looks very familiar. And it's going to be the thermal diffusivity, or the inverse of it rather. So thermal diffusivity is k over rho Cp, which is the inverse of what we have down here. And so we're going to say this is 1 over alpha. So this would be the heat diffusion equation in Cartesian coordinates, and is the final answer that we've been looking to derive.